Hello, everybody. Welcome back to this is week one, part two of the Intro to Biomedical Sciences. We're going to be talking about work and energy in human biomechanics. I want to quick say thank you so much for watching the first episode, the first video in this series. If you're looking for any way to potentially support the production of all these, first and foremost, like the video, subscribe to the channel, watch the whole video if you can. It helps out a lot. As well as I'm producing these worksheets along the side, kind of going through everything that I'm using. That you can obviously see them here. If you want access to this, as well as any of my other materials, for example, another popular video series that I have is the biology of cells and tissues. I do offer up all of my materials for purchase at a very, very reasonable price. In the description down below, there is a Google form link that you can fill out, as well as that has my contact information, everything in there, if you ever want to reach out or have any other questions. Without further ado, let's jump in. So we're going to start with the learning objectives. We want to do an overview of energy, then understand energy conservation. I tweaked a little bit the objectives, like the order of them, just in an order that made a little bit more sense. We'll look at energy conservation. We'll look at work as defined in physics. We'll relate work to kinetic energy, talk about examples of potential energy, talk about fundamental forces of the universe, and then finally add in the concept of time to talk about power. There is a good amount of what I would say equations and math in this chunk of material. I'm going to do my best to kind of go through all of them, make sure that we understand what's going on, as well as how we get to where we are. So the overview of energy in general, when we talk about energy, we define it as the ability to do work or to cause change, to make something move, to change shape, to do something that is different. We'll talk specifically about what work is in just a little bit, because it's a slightly different definition than what we're used to. Along those same lines, we're talking about energy. Energy is really unique in the sense that once we have energy, energy never goes away. There is a set amount of energy in the universe, and we can neither create nor destroy energy. We can only transform it. So, for example, I can pick up this marker, and I can hold this marker up by raising the marker. I'm taking kinetic energy, which is our motion energy, and turning it into potential energy, gravitational energy, all the way up. So if I bring it all the way up, I'm actually using chemical energy from my muscles, breaking down ATP in order to move this pen, move it all the way up here, and now it's changed the different forms of energy. So that's what we're going to be focusing on is the transition, the changing of energy to all the different states. There are a couple of different forms of energy that we want to be aware of. For testing purposes, the big thing to do is understand each of these types of energy, as well as their definitions. Okay? We essentially sort everything into kinetic energy and potential energy. Even down here below, chemical and electrical energy are technically under the umbrella of potential energy as well, but depending on which physicist you talk to, they're not always, it's not super cut and dry that it's all potential energy, because depending on the exact situation and how it's actually described. So for testing purposes in this course, understand chemical energy, electrical energy, these guys are all under the umbrella of potential energy. But out in the real world, that might not be a hard truth. Okay? So kinetic energy, this is the energy of moving things. When things have motion to them, they contain kinetic energy. So the faster something is moving, it has more kinetic energy. The more mass of that moving thing, more kinetic energy. Well, there is an equation for kinetic energy. That is, kinetic energy is equal to 1/2 of the mass in units kilogram multiplied by velocity, which is in units meters per second squared. 1/2 mass velocity squared. So just this was saying, increase the mass, you increase kinetic energy. Increase the velocity, you increase kinetic energy. And that's really what we're going to be looking at. And these are specific equations. What I would do, and I would start right now, is grab a piece of paper or open a special specific document and start writing down all of these equations. Having yourself a nice, neat, organized equation sheet is going to be crucial for when you get to exams, when you're prepping for quizzes, that kind of stuff, because then it's all in one place and you can see the connection between all of these things. So as I go through, I'm going to tell you, hey, add this to your equation sheet, and you should add them directly too. And I would highly recommend add them just like this, where you have the equation, and then below you have what each variable means. So m is mass in kilograms, v is velocity meters per second, ke equals kinetic energy, which would be in kilogram meters per second, would be the units on that. Actually be kilograms meters squared over seconds squared, I believe is the technical units. I'll have to look that up exactly. It translates to another unit. We'll see. I'll look at that later. So that's kinetic energy, the motion. Potential energy is stored energy that a system has due to position, shape, or configuration. Think water behind a dam, a stretched rubber band, a spring, this pen that I can just drop and it immediately goes all the way down. It had potential energy and then it converted it to kinetic energy. All those kind of things are potential energy. We have gravitational, we have elastic, we have thermal energy, heat energy can be stored. Chemical energy, we have chemical bonds that can be broken. The most common one that we're going to talk about is ATP, adenosine triphosphate. This is our body's chemical energy storage, chemical energy source, what we produce, what we put energy into, and what we use for all of our energy needs. Talking about chemical energy as well, we want to mention these words: metabolism. Metabolism is the chemical process where all living things make everything inside of them to maintain life. And there's two parts. There's catabolism, which is breaking stuff down into smaller parts. So breaking bonds, releasing energy. Then anabolism, or anabolic, where we make new bonds and we put things together and we actually put energy into them. Metabolism is our whole body is this fine balance of breaking stuff down and putting stuff together in order for us to survive. Additionally, we have electrical energy. Electrical energy is thanks to energy from moving electrons. That will be super, super important later when we talk about biochemistry and you get into the processes of making ATP, known as glycolysis, the Krebs cycle, and then the electron transport chain. You'll see all of that in the future. Again, talking about the transformation of energy. All of our day-to-day activities, everything revolves around transferring or transforming energy. For example, in our body, we use energy from electrons to create movement, so kinetic energy in hydrogen molecules, which then we use that kinetic energy to create chemical bonds in ATP. Then ATP is going to release that energy by breaking those bonds. So we're constantly in this back and forth between kinetic and potential energy. A minute ago, I mentioned this word called the system. I'm going to jump ahead a little bit. When we talk about the system, this is referring to a predetermined space. It can really be anything. So for example, we could say, oh, the universe is a system. The earth itself is a system. Our body is a system. A single cell is a system. This water bottle in here, the inside with the cap closed, inside of this is a system. We're just taking that, when we say a system, we're just talking about a predetermined space. Oftentimes we like to think of that system like a little box, like an airtight box that we seal up whatever it is that we're observing in there, so that way nothing is leaving the box. So a lot of times we'll say that the energy is conserved within the system. So within that little box of space, we're saying all of the energy stays within there. It just might transform into other forms, right? It might go from kinetic to potential. From potential, it can go to gravitational. From gravitational, it can hit something and transform into sound energy, heat energy, etc., etc. Okay, and we'll touch on that again in just a little bit. But that's a concept that can be a little bit confusing, so I wanted to touch on that right now. So back to our sort of example, we're constantly in this back and forth between kinetic and potential energies, where it's constantly movement to storage, from storage to movement, movement to storage, storage to movement, and so on. The example that is used in the PowerPoint, they do a couple different examples. The one that I like is this slingshot right here. So the slingshot, when we stretch the rubber band, we stretch that rubber material, that is taking kinetic energy. We're using movement to store up potential energy in the elastic. When it's released, all that potential energy turns back into kinetic energy, is transferred to the ball. Ball shoots up to the sky. As it goes up higher and higher and higher, it's changing from kinetic energy back into potential energy, in this case, gravitational potential energy. It goes all the way up until it hits the top, and then it comes all the way back down. Same thing, we can do the same exact kind of process talking about squats or with jumping. It's all the same. We're converting movement into potential energy. So we go motion to potential, from potential to motion, and back and forth. That's a lot of what is happening. An additional component to all of this, we talk about friction. Most people understand friction as when you rub your hands together and everything gets warm. That is friction, and friction produces heat. So essentially, the movement, the force of the interaction between the parts of your hands when you rub your hands together like this, that causes vibration of the atoms, and increasing that vibration actually produces a stronger vibration and produces heat. We're going to talk a decent amount about friction in the future. Right now, what we just need to know is that friction produces heat, and then friction also opposes movement. Anytime we try and move, friction tries to keep us back. It tries to stop us. Every time that we try and push a box across the floor or slide something across the counter, friction is trying to stop and oppose that movement. So we'll see friction again in a little bit. Now, so that is all of the kind of general stuff about energy. Now we're going to move into work. Remember, we said that energy is the ability to do work. So what is work? In physics, you need two things to be considered work. You need a force acting on an object, and that object has to move in the direction of the force. Okay? I should clarify, not this direction. It should move along the same axis as the force. So work literally is the transfer of energy by a force on an object as it is displaced. So you have to have a force and you have to have movement along the same axis. So for example, my water bottle, let's put this down right here. If I apply a force, a horizontal force to my water bottle, let me, little live action real quick. If I apply a horizontal force to my water bottle, let's say I'm starting to press right here, I'm applying a little bit of pressure onto it, but not enough to overcome friction. So even though I'm applying a small amount of force, there's no movement, no work is being done. As soon as it starts moving, now we are working. Work has to have force and movement along the same axis as the force. Whether that is in the x-axis, the y-axis, or the z-axis, again, it just depends on the force that we are using. The equation that we use for work is work equals force multiplied by displacement. And then again, force is, let's write these, force times displacement. Force is measured in newtons. Displacement is measured in meters. So we always have to be careful. Sometimes they'll give us numbers in centimeters. And so we need to make sure that we convert those to the proper unit of meters anytime we're doing any of these equations. When we have a force, when the direction of the force and the displacement are in the same direction, we call that work is a positive value. When the direction of the force and the displacement are in opposite directions, we say that work is a negative value. The force and the displacement being in the same value, that's like my finger pushing on the water bottle. The opposite force, or the negative work, would be being done by the friction force of the water bottle against the table that it's on. So the way that it kind of gets tricky when you want to word these things. So you typically reference the force as well as the axis when you are talking about work. So for example, if I, because this is sliding horizontally, that left and right plane, that's the x-axis. With that, we're saying that my force is the F, and then you'll do like the little x, and then the displacement is the D, and then a little x, so displacement in that same axis of movement. So the work of that force is positive. Because there's friction, and friction goes and opposes it and goes the opposite direction, the work of the friction is in reference to the friction, the work is a negative value. If that's a little bit confusing, don't worry, it's okay. Just know what I have written here, that when force and displacement are in the same direction, work is positive. When the force and displacement are in opposite directions, work is a negative value. That's what you're going to be tested on, is mostly the general basic understanding, not as much the total concept. So don't worry too much if it's a little bit confusing. Work, our unit of measurement is joules. And if we look, force is newtons, displacement is in meters. So we say 1 joule equals 1 Newton meter. Again, always check your meters. Make sure you're in meters and not centimeters before you do your work. This is an example question. I will say this picture, bad etiquette. Never really sit behind your patient like that if you can avoid it. And typically, yeah, I'm just gonna. I don't like this picture personally. I think it shows improper etiquette when palpating a patient. However, it's just a cartoon. So moving on. This is an example question. So when palpating someone's back, on an average force of 75 newtons is used to move the tissue by 1 centimeter. The work done on the tissue is blank. So immediately we look. First thing we want to do is pick the equation that it's asking for. So we're looking for work. Okay. So with work equals force times displacement. Do we have force and do we have displacement? Yes, we have 75 newtons and 1 centimeter. Pause, hold on a second. Centimeters, we need to be in newtons. So let's convert centimeters to meters. There's 100 centimeters in a meter. So this is now 0.01 meters. So 75 multiplied by 0.01 gives us 0.75 joules for our work that we have done. See what we did? Just those are the general steps for when we're calculating these types of questions. Pulling in a little bit of the information that we learned in part 1, unfortunately, the world is not two-dimensional. We're going to have different angles of forces. We're going to have diagonals and angles of forces that are not just perfectly straight up and down, straight or left and right. You're not going to be required to calculate a lot of this stuff. However, adding these two components together, this is all from part 1, where remember we could say if we have a diagonal force, we find the theta, which is the degrees between the ground essentially and where the force is acting on. So the x-axis and the y-axis. And then we could use the equations. The force in the x direction equals the force multiplied by cosine theta. The force in the y direction equals the force times sine theta. So if they were to give you this specific equation, except that this is a 75 newtons, an average force of 75 newtons at a degree of 15 degrees, then we could take this and we could calculate the x direction, we could calculate the y direction, and so we can calculate the amount of force, the amount of work done in the y direction, and the amount of force done in the x direction. Kind of taking what we just learned before and adding it into this. Again, I don't think that this course is going to force you to do a lot of this, just because it's a couple of extra steps that we don't really need to get too deep into, but just in case, now you understand how to do that. This is another example right here of what we just talked about. So the lawnmower, again, we talk about work. Work only counts when we're talking about the displacement along the same axis as the force. So lawnmowers, in this case, moving forwards and backwards, let's call that the z axis. So, or we'll say this is in two-dimensional land, so we'll call this the x-axis for now because it fits with our formula. The work done by the force F on this lawnmower is force times, one sec, that's okay, that's why this is supposed to be like this. There we go. That's why that was looking weird. So the force in the displacement direction is cosine theta. Okay, I'm just gonna erase this whole thing. This does not look right. We're going to calculate, so the force is down in this direction. So we have our theta. We want to figure out this d direction. This is the direction of our displacement. We're going to call this x. So we take our equation, f of x equals f times cosine theta. So f cosine, I'm just going to use O for theta right now because I don't know exactly where the symbol is. This would be our force. And to calculate work, we need to multiply by displacement times displacement. There. That looks a little bit nicer. The way that you write these equations definitely matters. If you write them nice and neat, you're going to have a much, much easier life when you go to solving stuff like this. Okay. So there we have it. We calculate the direction, the amount of force being used in the direction of the displacement. We multiply that by the total displacement, and that will give us the calculation. In these cases, for example, this is the briefcase. The briefcase is not moving, even though we're matching the amount of force that gravity has downwards. If you were to actually draw the other arrow in here, so this force is what you're pulling on the briefcase on. Gravity is pulling the same amount down, so it's balanced. It's not moving at all. No work is being done here. In this case, we're walking with the briefcase. Again, the briefcase is where the force that we're acting on it is straight up, but the way that it's moving is in the x-axis. So y-axis straight up, x-axis across is where it's moving. So no work is being done from a physics standpoint. If we're carrying it upstairs, now we look at it. Okay, now we have a force and displacement where we have the force is straight up, but our displacement is at an angle. So technically we have part of our displacement is also up. So we can use that however much we displaced upwards with the force that is straight up in order to calculate the amount of work being done. Okay. That was a lot. I know. Work is a little bit yucky, and a lot of this stuff it's a lot of equations, but we're getting through it. Let's see, where are we in the PowerPoint? Okay, now relating work to kinetic energy. This is through the equation that work is equal to the change in kinetic energy. So we'll take like the initial situation. So right when we start to act on like what the initial situation of everything is, the force is acting on, in this case, we're pushing a box. Whatever like the mass, the velocity, the movement, everything is at the very beginning when we very first start to act on that we start to apply a force to the box, and then we compare it to a separate time, what we'll call the final instance, and we compare those two. That is what it's talking about in change in kinetic energy. Anytime you see change in, that's represented by this triangular symbol. That symbol is called delta. So work equals delta, so the change in kinetic energy. This is another, these two bullet points are again more just to memorize, to know the concept, because it's exactly what is going to pop up on an exam. So if the displacement is in the direction of the force, the work is positive. We already talked about that. We already know that one. So we are adding kinetic energy to the object. As a result, it speeds up. We get increased velocity. So if we're doing positive work, it increases speed, aka velocity. If we're doing negative work, it's slowing down, velocity decreases. Okay, now a bunch of math type stuff. We're going to look at how these equations all sort of line up to give us a different equation. So we have work equals force times displacement. Force, if you remember from the previous part, Newton's second law of acceleration states that force equals mass times acceleration. So we can combine these two, replace force for mass times acceleration. Work equals mass times acceleration times displacement. Another rule of equations states that acceleration equals delta velocity, so the change in velocity, over the change in time. So we plug that in. Work equals mass times that change in velocity over change in time multiplied by displacement. This next step is where we can lose a lot of people. And so I literally wrote here the way that you get from from step G to H is through a bunch of calculus that I'm not going to get into. We don't need it for this class. We're not going into calculus. So just trust me when I say it works so we get here. Okay? So it's displacement multiplied by kinetic energy equals mass times change in velocity divided by change in time multiplied by displacement. We have that other equation that we're going to bring in, that the kinetic energy equals 1/2 mv squared. From all of that, we plug in the 1/2 mv squared into that chunk, and then this whole chunk in equation can be broken down, as we all went through, back into work. So work equals displacement 1/2 mass times volume squared. Did we need to do all of this to get this? No, I don't think so. I think all of this is kind of stupid that we had to do all of that. Now that we've gotten here, we can just use this equation. Okay, ignore all of this other stuff and just use this equation. Work equals displacement multiplied by 1/2 mv squared. Okay, it works. It's just the way that it just works. I hate that we had to do all that just to get to that point, but it is what it is. Next point, we talk about potential energy. There's not a lot of flow through all this material. A lot of this is just kind of just taking a lot of general physics type principles and smashing them all together. So the way that I would approach learning a lot of this is treat each of these learning objectives almost as like its separate little chunk of material, and learn each individual chunk by itself and connect what you can, but prepare that way for the test. Look at each individual section like it's like your chunk, an individual chunk of information. Okay. Exemplifying potential energy. We're going to look at gravity, potential energy in general again, and then at non-conservative forces. So gravity is an example of what's called a conservative force. I guarantee you this is going to be a test question. Gravity is a conservative force, which means that it is a force where the calculation of work depends only on the starting and the ending points and does not take into account the path taken to get there. So it does not care if you went down these valleys and up these hills. It doesn't care if there was a straight line there. It doesn't care if you hiked up a mountain. Conservative forces only cares the very beginning position and the very end position. So we use this equation. The gravitational potential energy is equal to the mass of the object multiplied by the gravitational acceleration constant. So this G is always 9.8 meters per second. Never changes. So 9.8 meters per second is your G value. So that is a given. You'll always know that. H sometimes is written as Y. That is the height along the y-axis, the vertical distance of the object above a reference point. And this is how we calculate the gravitational potential energy. So again, going back to that pen that I was holding before, if I wanted to figure out, okay, how much potential energy is in this pen when I hold it 4 feet above the ground, let's say 1 meter for easiness sake. Let's say the mass of this is going to be, being generous, we're going to say it's 1 kilogram. So 1 kilogram mass at a height of 1 meter multiplied by the acceleration due to gravity, 9.8 meters per second. So our potential energy is 9.8. That at 9.8 kilogram. Let me real quick look up what the specific units are for that. It's in joules. So all this works out. Measured in joules. So that works out. So it has 9.8 joules of potential energy. That's how you solve for a situation like that. There's a lot more information here on potential energy. Again, there's a lot of info here that's kind of confusing. It's just kind of a lot of randomness all strung together. The point of this slide here is to show you that there are different types of potential energy, and that amount of energy is the total energy is always going to be conserved, which means, again, we have our system. So the total energy in that little box is going to stay the same. It's just going to transform into different types. The equation that we use for this is that total energy equals our kinetic energy plus our potential energy. So we can calculate each of those, and they should add up to give us the total energy. And that should always be the same. The total energy should always be the same, no matter what. Okay? So one of the problems that it gives us, for example, is this baseball question. If we throw up a baseball, the initial velocity is 20.0 meters per second. It has a mass of 0.15 kilograms, and it's going to go up and up and up. And as we all know, eventually it's going to stop at the very top and come back down. So it's asking how high does the ball go? So we can calculate this by saying, okay, what is the total energy at the beginning? How much of it is potential? How much of it is kinetic? And then we can look at when it's all the way up as to the very top. That's its end point. How much energy does it have? And how much of it is potential? How much of it is kinetic? So we look at our equation. We say, okay, the potential energy I initial, so the potential energy at the beginning, plus the kinetic energy at the beginning equals the potential energy at the end plus the potential energy at the end. We know at the very beginning, in reference to the hand, we say, okay, the potential energy here is 0. All of the energy is kinetic. So it is 0 plus the kinetic energy. And then at the very, very top, again, we also know that our kinetic energy at the very, very top is 0 because it's not moving. The velocity is 0, so we got nothing up there. So now we come up with the equation 1/2 mv squared, and this is our v initial. So the velocity at the beginning equals the mass times the gravity times the height, because those were the different, our potential energy for gravitational potential energy. That was our equation for that. And this was our equation for our kinetic energy. And now we just plug and chug. Plug in the mass, we plug in the velocity, we plug in the constant for gravity, and we solve all the way down, and we end up 20.4 is the height. 20.4 meters is the height that this ball travels. That's most of the questions that you're going to get asked. Some of this other stuff, something that I breezed past was this elastic equation. This is just more of an FYI saying like, hey, this is another type of equation that we use in case we're involved with springs. For some reason, physics really likes to mess with springs. I don't get it. Whatever. But you have this equation up here, potential energy. This is UK, potential energy of a spring. They use K for springs. Again, I don't know why. K is a spring constant. They solve that based on this type of the spring that they're using. X is how much the spring is displaced. Plug those values in, and it gives you how much potential energy it has. Don't complicate it more than that. Okay, now we have non-conservative forces. Gravity is one of our conservative forces, meaning that the path doesn't matter. Non-conservative is the opposite. The path matters. That's going to be the test question about non-conservative energy. The other question about non-conservative energy is going to be that it is that friction is the big one. It's always negative because it opposes motion, and it's always decreasing the total amount of energy. Again, draw a line right here. New chunk of material, switching gears. Fundamental forces. Most of this is just memorization. There's 4 fundamental forces in the universe: gravitational, electric, magnetic, and nuclear. There's a weak and a strong nuclear force. All of these 3 forces these all decrease with distance. They are distant dependent. That's going to be the test question. They are also conservative forces. And another note is we often combine the electric and magnetic forces and call them electromagnetic forces, or electromagnetic force, because they are super interconnected. And that's, draw the line right there. Draw the line, new chunk of material. Now we're going to add in the concept of time, because we can do work, right? We put energy into something to get it to move, and then we need to ask, okay, how fast or for how long are we moving it, and how quickly does this work get done? And that is what power is. Power is the amount of work done in a specific amount of time. There's 2 formulas to calculate it. Power equals work divided by the change in time, so how much time we spent. Or it is power equals the change in energy over the change in time. Delta T, this change in time, typically is referring to how many seconds did you measure. So wherever you start measuring, that counts as your 0 mark, and then you measured for 6 seconds. So our delta T is 6. We measure power in watts 1 watt is equal to 1 joule per second, also equals 1 Newton meter per second. We can also kind of flip this script and say 1 joule is equal to 1 watt second. And doing the fun conversions of stuff, we can convert watts to kilowatts, seconds to hours, and that gives us kilowatt hours, which is how we measure power usage in the house. 1 calorie, little c, is 4.184 joules. They will always ask this question because they're gonna try and trip you up. The difference between the big C and the little c. Little c, 4.184 joules. Big C is equal to 1,000 little c calories. So that is 4,184 joules. Keep forgetting to move the actual slides. We talked about friction, we talked about those forces, we talked about power, values. Efficiency, this is referring to the percentage of work that's put into a machine that is converted into useful work output. Another equation, throw that equation into your equation sheet, because you're going to have a question that's asks what's the efficiency of this, and it'll give you these values, and you need to calculate the efficiency. Again, energy is converted into lots of different things. Probably a good idea, know these specific examples. I could see a professor asking you specific questions, talking like elastic into sound is an example of what, or an example of converting elastic energy into sound energy is what? The string oscillating on a guitar. I could see a question like that popping up. Energy is transported either through waves or through fields. That's really all that we need to know from this slide. And that is all of the material. Last little comment talking about if you see the word biological energy, this is the body or the organism converts chemical energy originally from food into kinetic, gravitational potential, and other forms of energy. Just a little definition type thing. Okay, this was a pretty long video. Hopefully, the majority of it makes decent sense. It's been a while since I've done a lot of the physics stuff, and with all of the little math and wanting to include calculus within physics, calculus and physics go hand in hand. So I tried to avoid bringing a lot of that calculus into the physics stuff. All right. Thank you guys so much for watching, and have a wonderful day and good luck studying.